Chemistry, we're following up our lesson on weak acids with a lesson on weak bases. There's a lot of similarity between how you deal with the two, so this will be a fairly short lesson. So the base can be the conjugate base of a weak acid, such as acetic acid. So there you see it. You have the acetate ion, that's CH3COO-. We saw that quite a bit in the last lesson. Plus water. And what that acetate ion will do, it's a weak base. It will occasionally pull a proton away from the water molecule. That will turn the acetate ion into an acetic acid, CH3COOH, and it will leave that broken water molecule behind as an OH-. It's the water molecule minus one proton. So that's a hydroxide ion, and that's what characterizes a base. Anything that creates OH- in solution, in water solution, is a base. So this reaction can be written in the generic form, A-. So A- is the acetate ion up there, plus H2O. And then once you add that proton back to the acetate ion, it becomes acetic acid, so that's HA. It's no longer a negative charge, it now has that proton added on. And then you still see the hydroxide ion. A- in this case is the acetate ion, which can attract a proton and act as a base. Acetic acid and the acetate ion are a conjugate acid-base pair because they differ from each other by one proton. That's the definition of conjugate acid and base. So CH3COO- uses A- in its generic form because it is an ion. Here's an equation for a weak base equation involving ammonia. Now ammonia is a weak base. So if you take NH3 plus H2O, occasionally, it'll take a proton away from H2O, and that proton will jump onto the NH3 and turn it into an NH4. Remember, the proton represents a hydrogen, and since it didn't bring its electron along, it has a positive charge. So that molecule is called ammonium, and that's NH4+. And what it leaves behind is the broken water molecule, and that's the hydroxide ion, OH-. This reaction can be written as a generic reaction as follows. B plus H2O produces B, the base, plus the proton, H+, and the hydroxide, the OH-. B represents the base NH3 in this case. BH+ represents the conjugate acid NH4+, that's ammonium. Now, NH3 uses B rather than A- in its generic form because it's electrically neutral. So if the base is a conjugate base that has a charge to it, a negative charge to it, such as acetate, then it uses A-. If it doesn't have any charge, ammonia doesn't have any charge, it's electrically neutral, NH3, so then it uses B as its generic representation for a base. Okay, so now we're going to just do one example here. We're going to compute the big four here, pH, pOH, hydroxide concentration, hydronium ion concentration. And again, 3.2 molar is just a random number that was selected for this problem. Molar concentration, and this is a base, C5H5N. How do you know it's a base? You'll either be told it's a base, or one way you can know is look at the equilibrium constant there. That's the base dissociation constant, Kb. That tells you that it's a base. So let's go ahead and do this. So let's fill out the Rice table, complete the reaction with the base pyridine, that's what this is called, accepting a proton from water to create OH- and enter the initial concentrations. Okay, so step one, we're going to complete the reaction with the base pyridine, that's what this base is called, C5H5N, accepting a proton from water to create an OH-, and we're going to enter the initial concentration. So for the pyridine, it's 3.2 molar. We don't count the water. We have initial concentration of the conjugate acid there, CH5NH+, of 0, and of hydroxide of 0. Now the change, again, with acid-base reactions, almost always the coefficients are 1, so it's going to be, since there's no concentration values are given for CH5NH+ and OH-, we can assume they're 0. So now we're going to go ahead and enter the change line. So enter the variable x on the change line with coefficients plus or minus sign. So coefficients again are always 1, so it's minus 1x. Product side it's plus 1x and plus 1x. The reactant C5H5N shows a negative sign because it is decreasing in concentration. The coefficient in front of the X variables are the same as in front of the reactant and products above each, and they're almost always ones in acid-base reactions. Water is not included since it is a pure liquid. Okay, add and subtract the change line from the initial line to get the equilibrium. So 3.2 minus x, 0 plus x is x, 0 plus x is x. Okay, write the law of mass action. So if the value of Ka had been given, you would need to convert it to a Kb value, and that's using the formula Ka times Kb equals Kw, which is 10 to the negative 14th. But it wasn't given. A Ka wasn't. You were given a Kb, so you can go ahead and use that since this is a base reaction. So there's the law of mass action. Be sure you understand how that was formed. You don't use the water, H2O. Okay, now we substitute the algebraic expressions on the equilibrium line into the equation, and we go ahead and put our actual value for Kb in there. So there you go. You have x times x over 3.2 minus x. The simplifying assumption states that if the value of x is much smaller than the initial concentration, 3.2, in this problem, then x in the 3.2 minus x can be eliminated. So we're going to go ahead and do that and use the 5% rule at the end to justify it. We're not going to actually calculate that, but we'll just take a look at the final answer. So there you go. There's the equation from the last slide. And you simplify it to x squared. X times x is x squared over 3.2. Now it's just an algebra problem to solve for x. So there you go. You multiply both sides by 3.2. Cancel on the right side. You get x squared equals 5.44 times 10 to the minus 9. Take the square root of both sides, and you end up with x equals 7.38 times 10 to the negative 5th power. And that x represents the OH minus the hydroxide concentration, 7.38 times 10 to the negative 5th power. So you can see that x is much, much smaller than 3.2. I mean by 100,000 times. And so therefore the simplifying assumption is easily met. Calculate the concentrations, and we're going to do all of them. So there's the concentration of C5H5N. You take 3.2 and you subtract x from it, and that gives you effectively 3.2. Again, x is so much smaller than 3.2. To two significant figures there, it doesn't change it at all. Now there's the conjugate acid there, and that's simply equal to x. Based on the equilibrium line on the Rice table, x is the equilibrium value of that conjugate acid, so it's 7.38 times 10 to the negative 5th, and the same is true of the hydroxide, and that's going to be 7.38 times 10 to the negative 5th molar. Okay, now we're going to calculate the H3O plus pH and POH concentrations. So for H3O, H3O plus hydroxide times hydronium equals 10 to the minus 14th. You know that formula. And that's going to do a little algebra to get the hydronium ion concentration. And it's going to give you this, 1.4 times 10 to the negative 10th. That should be a capital M after that for molar. For the pH, it's negative log of the number you just computed, 1.4 times 10 to the negative 10th. That's the hydronium ion concentration. That gives you 9.9. That's well up into the base range. It's not a strong base, but anything above 7 on the pH scale, 0 to 14, is going to be a base. So 9.9 is kind of a weak base. And now the POH is going to be POH plus pH is 14. Just subtract the pH from 14, and you get the POH, which is 4.1. And that takes care of this example. You can see it's done very much like a weak acid. These problems all start to look the same after you've done a few of them. So practice these, and this subject won't seem quite so difficult.